Okay, so what if we have two things here? We have that tan theta is y over L, and we have that d sine theta for constructive interference, d sine theta is m, which is just the fringe number, whole integer, times lambda. So L is the distance to the screen. If I increase the distance to the screen, what's going to happen to this theta? So if my denominator gets bigger, what happens to theta? So if the distance to the screen increases, then theta does what? It decreases. Very good. Now if theta is going to decrease right here, that's not a big deal. All right, let's look at another thing we can manipulate. We can manipulate the distance to the screen. That's easy to manipulate. We can also manipulate what light or what sound wave we were producing, so the wavelength. So if let's increase the wavelength. If we increase the wavelength, what's going to happen to theta if we increase lambda? It's going to increase. It increases. See if, nope, it's not ready to play with me yet. What did I change? We changed the wavelength. We increased the wavelength. What's happening to y as we increase the wavelength? So here's our first wavelength. And you can see the angle right there. Or it shows us the angle. It goes from 11 something to 23. So what's going to happen? It's going to increase. So y will increase. Now look to see what happens when the spacing between the slits, let's see, well, let's look at the distance between the slits. That's something else we can change. What happens is the distance between the slits increased. I'll go back down here. It's pretty much one opening right now. We increase the slits, the separation, and what's going to happen to the angle? It's going to decrease. So over here, if we increase the distance, we decrease the angle. And if theta decreases, what happens to y? It also decreases. There's a direct relationship between y and theta. Maybe. Now let's look at the spacing when it's really, 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 really small. Do you see one fringe? Yeah. Now let's take our wavelength and use a smaller wavelength. But we get kind of a very interesting pattern. Okay. The pattern actually can be described as a single slit interference pattern. This is kind of a cool little app there. Whoa, totally right. Alright, so this is you holding the laser beam. This is a slit. So one X-Acto knife strip. Okay? Here's the screen, and this is what we see happen to our blue laser light on the screen. We see a bright fringe, two dark fringes, bright fringes, and what's different about their intensities compared to when we had the double slit? they start getting weaker, right? All right. If I increase the wavelength, we see that they get further apart. If we make the slit really skinny, we get one big kind of blob in the middle. If we make it really, really fat, we get a pretty intense little variation there. And then if I'm going to put this back in the middle. If we move the screen away, see how it's scooting back in the picture? So it's kind of like we're zooming out, zooming in, zooming out, zooming in. No? So when we change the slit difference, we can also change the width of this bright central fringe. So a single slit can also cause an interference pattern, and it's very similar to the double slit, except for you get a central bright. So if I had we have blue again here, we'd have our central bright, pretend like that's in the center, and then we still have that fan type shape where we have another bright interference there, a bright interference there, but our brights are getting weaker. Our bright interference there. Now what happens, I'm going to zoom in. So here, you know how sometimes you see a little inset in a textbook? So there's my little red dotted line, circle, and then I'm going to have my little inset right here. So here is the opening, enormous and open like that. And so as the wave gets here, it actually starts bending around this edge. And so each one of the edges behaves kind of like a slit itself. And so we'll get an interference pattern with it too. And that interference pattern will look very similar to the other. But we'll have a central bright in the middle. So this will be our central bright in the middle. And then we'll have our bright fringes above and below, but they're getting weaker in intensity. I didn't do a good job drawing that screen, did I? So there's another bright here, and a bright here, and a bright here, and a bright here. But there's also a dark here, and a dark here, and a dark here, and a dark here. And as this wave is bent around this edge, the wave that's bent around the edge here, it has to, we want the path difference for these two guys, so as they go to meet each other, so from the very center of the opening there to this dark fringe there, and from the nope, not the center, that was a bad thing to say, from the top of the opening. I'll fix it. Okay, so from the top of the opening and from the bottom of the opening, those two waves, if I want to get a dark fringe there, what does the path difference have to be between those two waves if I want to get a dark fringe up here? What is the path difference if I want to get dark? Up. Okay, but our path difference needs to be multiples of half, so some half wavelength off. Okay, so lambda over 2 times m, but m has to be odd. And there's a better way to write that. I'm just lost right this second. So that has to be our path difference. Let me back up here just a second. This wave right here, let me fix it. this wave right here does not come from the bottom, but comes from the center. So if we look at, just delete this thing. So it's from the center right there when it gets all interfering. And so this distance right here, the width of the slit opening is D. So this right here is D over 2. Okay? So over here, if I can, I'm going to try to make this one look better too. No, I can't. Anyway, it should be coming from the middle of the opening. Anyway, so then that means that D over 2 sine theta is our path difference, is equal to M plus 1/2 lambda. So this is a true statement for any number of half wavelengths to be off, but in order for this first one to occur, the path difference has to be half the wavelength. So down here, all I need is half the wavelength here. And so this is still d sine theta is equal to m lambda. And m is the number of the dark fringe, because this was destructive interference.